Hello physics students, this is Dr. Brenzy here. This is lesson 3.1.6. The topic of our video this afternoon or evening or whenever you're watching this is what are called conservative and non-conservative forces. Now when we're talking about conservative forces, we're not talking about its political inclination, but we have a different definition of what conservative is in physics. But I want to define what it is before I actually talk about why we call it conservative. So when we think about conservative and non-conservative forces, we want to think about work done along two different paths. So I have a force being applied to this block. It's the same block as this one. And let's say that this block takes a path from here to here. What is the work that this force is doing on this block as it goes along this path? Well, the answer to that question is W equals F times the displacement, and the displacement is Y. So on this particular path, the work done by this force is F times Y. Now let's consider a second path. Let's consider a path that goes from here over to here, up to here, and then back, so that it ends up at the same point that our first path did, but we have some additional distance to go. And let's ask ourselves, what is the total work done by this force along this blue path? Well, the work done along this part right here by this force is 0, and the reason it's 0 is because our force is perpendicular to the path, and when a force is perpendicular to a path, it does no work along the path. So for this part of the path, the work that the force has done so far is 0. Now let's ask what work the force does along this part of the path right here. Well, it's going to equal F times displacement, because now our force is parallel to the path. So we just multiply force times displacement. Finally, along this third part of the path, again, the force is perpendicular to the path. And when a force is perpendicular to a path, that force does no work. So if I add these three up along this blue path, I get that the total work done is equal to F times Y. And that is the same as the total amount of work that I did along the red path. Oops, let's see here. Let me zip through that. Apparently I wrote all this down beforehand. Alright, so my second slide is a definition of what a conservative force is. So if the work done by the force is independent of the path taken, then that force is a conservative force. So if you go back to the force on my last slide, that would be an example of a conservative force because I took two different paths and I came up with the same amount of work done by the force along that path. I could have picked any other path as long as it goes from point A to point B, the same 2 points, and I would have discovered that I do the same amount of work. So that would have been an example of a conservative force. Now, if the work done by the force is dependent on the path taken, then that force is a non-conservative force. So, if I had a different amount of work done along those two paths, then that would have been considered a non-conservative force. So let's ask ourselves, is gravity a conservative force? So we have a block that's under the influence of gravity, and when it takes a path here, the work that gravity does is equal to F times y, and we can replace F with mg, so the total work done is m times g times y. Now let's go along this path, the blue path. Well, the work done by gravity along this part is 0 because gravity is perpendicular to the path. So that part of the path, the work is 0. And then it goes along this direction y. And now the force is parallel to the path, so we just multiply the two together, F times y, which is m times g times y. And then if I were to bring it back here along this direction, the force is again perpendicular, so that means that the work that the force does is 0. So if I add up the total forces, I have m times g times y. Here I have m times g times y. The amount of work that I do is independent of the path that I take. So is gravity a conservative force? The answer is yes. It certainly is. Let's consider a spring force. So is spring force a conservative force? Well, our spring force is equal to K times Y, so we can imagine having a spring hooked up to this mass. It's not necessarily hanging vertically. We can say that we're looking down at a tabletop here, and we can roll this left and right, and then we can stretch the spring and compress the spring. So, what is the work done along this path right here? Well, that is going to equal 1/2 times K times Y squared. That's the work done by the spring force along this path right here. Now let's think about the blue path. Well, the spring force is perpendicular to this part of the path, so the work done by the spring force is 0. And then along here, the work done is 1/2 times K times Y squared. And then down here, our force is again perpendicular to our path, so the work done is 0. So the total amount of work that I did is 0 plus 1/2 ky squared plus 0. Well, that total is 1/2 ky squared, which is equal to this. So I can say that this spring force is indeed a conservative force. Well, you're beginning to wonder, are all forces conservative forces? And the answer is no. So let's look at an example of a force that is not conservative. Friction force. So is friction force a conservative force? Well, let's figure out. We know that the force due to friction is equal to mu times the normal force. And we're going to assume that we are looking down on a tabletop. So we're going to assume that the normal force is equal to the force due to gravity. So we're going to say that our friction force is equal to mu times m times g. So let's calculate the amount of work that our friction force does along this path. Well, first we have to remember that friction force always acts against the direction of motion. So it is going to be pointing opposite of the displacement. So the work that I do is actually equal to negative mu times m times g, that's the force, times the displacement y. So what that means is that we are actually doing negative work with the friction force, which means that this is actually losing energy rather than gaining energy as it goes along this path. And that makes sense because as a block slides along a friction surface, it slows down, right? It starts to lose kinetic energy. Okay, so this is the work done along this path. Now let's figure out what the work done along this path is. Well, when we have friction force acting along this path, the direction of the friction force is opposite, again, of the direction of motion. So the work done along this part of the path is equal to negative mu times m times g times x. Now, along this part of the path, well, that's the same thing as what we had over here. W equals negative mu times m times g times y. And then when we go along this path, our force, friction force, is now in the positive direction, but our displacement is negative, so the work done is mu times m times g times negative x. And I can simplify that as mu times m times g times x. So if I add up all the work done along this entire path, I get mu times m times g times x. So I'm basically adding up all three of these terms. This is the first part, that's the second part, that's the third part. And when I add up all three of those together and then do some algebra to group like terms, or to pull out a like factor, a common factor, excuse me, I get this expression here, negative mu times m times g times the quantity y plus 2x. Well, that's certainly not equal to what I got on this path over here, right? So there is a difference in the amount of work that's done, and it's dependent on path. Therefore, friction is not conservative. It is not a conservative force. So, thinking about some other forces that you're familiar with, we know that gravity and spring forces are conservative. We know that friction force is not conservative. Tension force in a rope is conservative. And one other force that you're familiar with that is not conservative is the drag force. And as we get more and more familiar with different types of forces as we go on, we can figure out whether or not they're conservative or not. But these are the ones that we've been running into by far the most often. So what are some properties of conservative forces? So the work done by conservative forces has 4 different properties. And these are really important properties, and in a sense we've been using them already, but now I'm finally formalizing this for you and putting it into formal language. So the work done by conservative forces, number 1, is independent of path. So the work done by a conservative force is independent of the path taken. Well, that's the definition of a conservative force, right? Now, because it's independent of the path taken, the only things that matter when I'm calculating the work done by a conservative force is where I begin and where I end. So I can say that the work done by a conservative force equals the change in potential energy between the start and the end points. So, what do I mean by that? So let me write a little image over here on the side. So if I have a particular potential energy here, so let's just say gravitational potential energy, and then down here I have another potential energy. Let's say we'll call this UG2 and we'll call this upper one UG1. So no matter what path I take to get from here down to here, doesn't matter how curly and how crazy this path is, I can just say that the work that's done by this conservative force along this path is equal to UG2 minus UG1. The third property of work done by conservative forces is that the work done by a conservative force is reversible. In other words, if I go from this point down to this point, I gain some energy, some kinetic energy, But then if I decide to go from this point back up to this point, then I find that I am actually taking out what let me see here. Yeah, so I said we gained energy when we came from here down to here. So we gained some kinetic energy, if this is a gravitational force. And then when I go back up this path, up to this point, then I have lost that same amount of kinetic energy, and it has become gravitational potential energy once again. So the work done by a conservative force is reversible. So if I did some work W going from here to here, which is equal to the difference between the potential energies, then I would lose the same amount of work by returning from this point back up to this point. Okay, so that's what it means by being reversible. Last point is that the work done by a conservative force is equal to 0 as long as I have what is called a closed path, and that is the end of the path is where the beginning of the path is. So if I go from here down to here, and then I decide to go over here, and then I decide to finally make my way back up to here, the total amount of work I've done, or the total amount of work that's been done by this conservative force, equals 0. All right? So let's compare that to, or contrast that with non-conservative forces. Well, work done by non-conservative forces depends on the path taken. We can't even define a potential energy because we don't know how much work is done between one point and another because it depends on the path that we take. The work done by non-conservative forces is irreversible. Okay, so if I go from one point down to a second point, if I gain or lose some energy, let's say that I lose some energy going from here to here, like with friction. If I try to go from here back up to here with friction, then I'm never going to be able to gain that energy back that I lost. So any non-conservative force, the work done by a non-conservative force is irreversible. Once I've lost it, I've lost it. The work done by a non-conservative force is also non-zero if the path ends where it began. So if I start here and I do that little crazy path around here and I end up where I started, I will actually find that the total work that I did is not equal to 0. All right. Now, why is it called a conservative force? So finally I'm at it. A conservative force conserves the total energy, the kinetic energy plus the potential energy, if no other forces do work on the object that we're dragging through this with this force. Right? So that is why we call them conservative forces. It has nothing to do with whether it's conservative or liberal. It has nothing to do with its political inclination. Okay, one last slide, and that's just for those of you who have for AP. So if you're in advanced, you don't need to take these notes, but if you want to stick around, go ahead. So let's ask one last question. Is this force a conservative force? So let's say that I have a force that depends on this horizontal direction here. So when I'm at this position, the force is equal to F. But when I go over to this position, the force is equal to 0.5 times F. Well, I can calculate the amount of work. This is F times Y right here. All right, but if I go along the blue path, it turns out that the work done by this force along the blue path is 0 because it's perpendicular. Likewise down here, it's 0 because the force is perpendicular to the displacement. But over here, I have W equals 0.5 F times Y. And that's a different amount of work that I came up with than I did over here. So this would also be an example of a non-conservative force. Now, you might not think of a real-life scenario where you'll run into a force that changes as position perpendicular to the force itself. But you might run into, when you do electricity and magnetism, you might run into electric fields that change as a function of position. And that means that the force that that electric field has on a particle changes with distance or changes with position. So you might run into a non-conservative force that looks like this, but not in a mechanics sense usually. At least I can't think of one now. But I just wanted to make you aware of that. That's a situation that you might run into, especially on an AP exam, where it might ask if this is a conservative force, or it might ask you to calculate the work done and ask you if we can assign a potential energy to this force, which we can't because it's not conservative. Okay, so that's it for lesson 3.1.6, conservative and non-conservative forces. I look forward to seeing you soon. Bye.